In this video, we're going to learn about geometric series. This is a type of the series for which we can relatively easy confirm divergence or convergence. The geometric series has a special form. To better understand what that form is, let's try to take the geometric series that's written over here and expand it. So here I can see that terms that we're adding, they have the following form. So it's a times r to the power n minus 1. Well, n changes as we move from one term to another, right? So we start with n equals 1. That means that the first term is a times r to the power 1 minus 1. Well, 1 minus 1 gives us 0, right? And then r to power 0 is just 1. So that means that first term is just a. What is the second term? Well, it's when n equals 2. 2 minus 1 gives us 1. So second term is ar to the power 1, or just ar. Third term, n equals 3. When n equals 3, power becomes 2. So it's ar squared. And now you probably can see the pattern, right? So all terms. So what can we say about terms of the series? Well, it looks like each new term is obtained by multiplying the preceding one by r, right? So if I take second term, I can get it by multiplying the previous one by r. I'll get ar. If I'm here and looking at the third term, then it can be obtained by multiplying the preceding term by r as well. Right? That's how I'll get ar squared, and so on and so forth. So each term is obtained from the preceding one by multiplying it by r. And r is called common ratio when we work with geometric series or geometric sequence. Actually, these terms are terms of the geometric sequence. So r is common ratio. And now in the condensed form, the geometric series has the following form. It's constant a times r, the common ratio, raised to the power n minus 1. So it's only r that's being raised to the power n minus 1. A is not. So when we have geometric series, we should recognize it by observing this kind of form or by being able to put the given series in this form, and then this is how we determine its convergence or divergence. Well, if absolute value of r, and again this is like the base over here, right? If absolute value of r is less than 1, then geometric series is convergent. And in fact, we can even calculate its sum. So here's the formula for calculating what that series equals to. It's a, which is that constant, over 1 minus r, where r is the common ratio. Now, just a note here, what does this mean? Absolute value of r is less than 1. So r itself can be either positive or negative. But if we clear the absolute value here, we're going to end up with a double inequality. So absolute value of r is the same as r being between -1 and 1. So when r is between -1 and 1. And then geometric series is divergent if absolute value of r is greater than or equal to 1. If I expand that, then it means that r is less than or equal to -1, or r is greater than or equal to +1. So everywhere outside of this interval. And that's how we determine convergence or divergence. So let's do a few examples. In the first example, we need to determine whether the geometric series is convergent or divergent. And if it's convergent, we're going to find its sum using this formula. So first of all, let's confirm that this is the geometric series. If this series is geometric, each term can be obtained from the preceding term by multiplying it by a number, by the same number. So by what do we need to multiply 4 to get 3? Or by what do we need to multiply 3 to get 9 over 4? Or by what do we need to multiply 9 over 4 to get 27 over 16. Maybe that's going to be the easiest place to find that when we look at two fractions. So 9 over 4 has to be multiplied by what to get 27 over 16? 9 has to be multiplied by 3, and then 4 has to be multiplied by 4, right? Let's confirm that with the other terms. So if I check, let's check. If I take 3 and multiply by 3 over 4, what will I get? Well, yeah, I'm getting 9 over 4. That worked. And then if I take 4 and multiply it by 3 over 4, will I get 3? 4 times 3 over 4, yes, 4 and 4 will cancel, and I'll get 3. Okay, that works. So that number by which we have to multiply each term to get the next one, that's what we call common ratio. So R is 3 over 4. That's a common ratio. Oh, and yeah, by the way, in this example, we're not given our geometric series in this condensed form, right? It's just written out for us. It's this expanded form. So, but the way we determine whether it's convergent or divergent is the same as described in this definition. So we need to take the common ratio and think which case it belongs to. Well, it looks like it belongs to this first case, right? So 3 over 4 is between -1 and 1. And that means that this geometric series is going to be convergent. So since, let's write that, since, I'll just show how 3 over 4 is between -1 and 1, then the series is convergent. And since it's convergent, we can calculate the sum using the formula. So it's A over 1 minus R. Okay, so where do we get A from to use this formula? Now, when series is given to us using sigma notation, we know that A is this constant right next to the common ratio and its power. But the way we're given the series, it's actually in the expanded form. And we can see that when it's in the expanded form, A happens to be the very first term of the series. So that means that in our example, A is going to be the very first term, and that equals 4. So if I follow the formula, A is going to be 4. And in the denominator, it's 1 minus R. So we know that R is 3 over 4. That's R. And then what's left to do is just to calculate it. So that's 4 over 1 minus 3 over 4. That's 1 over 4. That's same as 4 times reciprocal of that. So it's 4 over 1. So that's same as 16. That equals 16. Well, and that happens to be the sum of the series. So if we add infinite many terms of this geometric series, we're going to get 16. That's going to be the sum. Well, let's try one more example. This time, the series is given to us using sigma notation. And we want to show if this geometric series is convergent or divergent. Now, to say or to determine that, we need to look at the common ratio. But to be able to see the common ratio or to find common ratio, the series has to be in this specific form. It has to have some kind of constant, and right next to it some base raised to the power n minus 1. And the base is what we call common ratio. So obviously we don't have our series in that form yet. So our goal will be to put it in that form. So I'll say goal, rewrite as sigma with n from 1 to infinity, AR to the power n minus 1. So that's the part that we need to obtain, AR to the power n minus 1. So I'm going to work on just the expression inside sigma. So I'm going to rewrite it 6 times 2 to the power 2n minus 1 over 3 to the power n. And this is how I'm going to work it out. I need to just manipulate the powers here. So I want to kind of like fix all the powers I have and make the power I need. So for example, I'll start with the denominator. This is how I can think about it. I have 3 to the power n. I want 3 to the power n minus 1, right? If I want 3 to the power n minus 1, then right next to it, I need to write 3 to the power negative 1, right? Because if I follow the rules for exponents, if I multiply those two bases, I will have to add the exponents and power will be n minus 1, right? But I cannot just multiply by anything I want because now the overall quantity changes. So to undo what I just multiplied by, I'm going to write 3 to the power 1 right next to it. So I wrote 3 to the power negative 1, and right away I put 3 to the power 1 right next to it. So what happens when I combine them together? Well, power becomes negative 1 plus 1, which is power 0, and then 3 to the power 0 is just 1, right? So in reality, I only multiplied by 1. So once again, I write what I need, but right next to it, I cancel it so that the overall quantity doesn't change. Okay, so let's continue. Now, 6, I'm just going to leave it alone for now, but to the power 2n minus 1, that's not the power I need. I need to fix this. So to fix that, I will first expand it, and that's how I'll write it. So I'll separate power 2n and then power negative 1. So it's 2 to the power 2n, and right next to it, 2 to the power negative 1. And always check if you can combine them and go back the previous step. Right? That's how you know if you're on the right track or not. Now, in the next step, in the denominator, I will combine those two bases so that I get what I really needed, 3 to the power n minus 1. And looks like I can actually simplify 3 and 6, right? I can divide out 3, then I'm only going to have 2 that's left. So that's 2, right, from here. Now, I don't want to have power 2n. I want to have just power n. And the way to separate 2 and n, since they're multiplied, it means that I have to separate them this way. In which case we multiply powers. Well, when it's power on the top of the power, right? So 2n means the same as 2 to the power 2 and then to the power n, right? And again, double check. If I simplify that, will I go back to 2 to the power 2n? I will, right? So that's how I fix that, so that I can obtain just power n. And then I also have 2 to the power negative 1 here. Well, let's say I'm going to put it in the denominator, so its power becomes positive, so it's just 2. It becomes 2 in the denominator, right? Okay, so what next? Well, next I can see how those 2's can be simplified. Now the denominator is 3 to the power n minus 1, and the numerator is 4, right, to the power 2. That's 4. 4 to the power n. Now, I don't want 4 to the power n. I want 4 to the power n minus 1. So I'm going to create power n minus 1 same way as I did for 3 on the bottom. So I'm going to write next to it, I'm going to write 4 to the power negative 1. Now, as I combine them, I'll get power n minus 1. But since I just brought it out from outside, I need to cancel it right away. So right next to it, I'm going to put 4 to the power 1. And that 4 to the power 1 cancels 4 to the power negative 1, right? So in reality, it's just 1. Now, what does this mean? It means that now 4 to the power n and 4 to the power negative 1, I can combine. It's 4 to the power n minus 1. That 4 stays. I'll just write it in the front, right here, 4. And then denominator is 3 to the power n minus 1. Okay, so finally I have power n minus 1 on the top and on the bottom. But remember, we want to have some kind of number times another number that we're going to call common ratio raised to the power n minus 1. We don't want to have several bases with power n minus 1. We need only one base. But what we can do here, we can combine 4 and 3 into one fraction, right? Remember that property of the exponents. So See how I'm gonna write it. 4 stays, but then 4 and 3 I'm gonna put together into the fraction 4/3, and then power n minus 1 is gonna be outside. And once again, simplify this. See if you can go back to the previous step. And we know that there is a property like that, right? 4 can be raised to that power and 3 can be raised to that power, and you go back. And finally we got that form, right? So let me put it over here. So that series can be written also this way. Sigma n from 1 to infinity. So it's 4 times 4/3 to the power n minus 1. So what is what in this form? Well, 4 represents A, and then R is 4/3. Right, this is R. I guess I don't really need the equal sign here. And that's when we can determine whether a series is convergent or divergent. So what can we say about R? Going back to the definition, it's 4/3, right? What can we say about R? Which case is that? Is it between -1 and 1? Well, no, it's not. It's actually this case. R is greater than 1. 4/3, it's greater than 1. So I'll make a note here. So R equals 4/3. That is greater than 1, or greater than or equal to 1. So that means that, what does that mean? Well, that means that this geometric series is divergent. The series is divergent.